Hi, everyone. For those of you that do not know me, I'm Srilata. I'm on the Deltec project, and I've been with Solution Street for over 5 years now. And today, I'm going to present Apache Spark as my tech topic. We're going to cover the basic framework, components, lifecycle concepts, and then why it is above and beyond the other similar frameworks in the market today, and then we'll look at some examples. What is Spark? So Spark is an open source, general purpose cluster computing framework. It was first developed in 2009 at Berkeley's AMP lab at the University of California, and then after a year, in 2010, it was donated to the Apache Software Foundation, and then they took over. And this framework, it does data analytics on huge data or big data. And this term, big data, is thrown around quite a bit. What is big data? How do you define big data? So one definition relates to the volume of data. It is too big by traditional standards. RDBMSs cannot handle them, cannot process them. And then another definition relates to the richness of data, wherein the data, it captures a lot of nuances of the entity that it represents. And it could be defined with the three V's, which is volume, velocity, and variety. And with variety comes different data sources from where the data is coming in. It could be structured, semi-structured, multi-structured, and also from disparate sources like data streams, databases, images, graphs, etc. So these are some of the big names that are using Apache Spark. Netflix uses Apache Spark so it can study or gain insight into users' viewing patterns and then throw out recommendations at them as to what programs or movies they would like to watch. And Yahoo uses it so it can personalize its news pages for users and also targeting advertising. And then Pinterest also uses it to gain insight into the interests of the user so it can bring in pins that match their interests the best. And Shopify, it was using its ETL data warehousing platform, and that did not meet its needs in the sense that it had huge data, which was to the tune of millions of records, and then their processes would time out because they were not able to handle that volume. And they've switched over to Apache Spark, and within a matter of few minutes, 67 million records were handled, and then they had their customer data that they wanted. And Conviva is another video streaming company next only to YouTube, and this uses Apache Spark so it can optimize and reduce customer churn while streaming data to it, so the users can experience high quality viewing. And eBay too, and then Alibaba, it's the world's largest e-commerce platforms that uses Apache Spark too. And then the top 5 use cases for Apache Spark, the numbers speak for themselves. So performance gains, ease of use, ease of deployment, advanced analytics, and then you can do real-time streaming, whereas Hadoop only provides batch processing. Then coming to the framework, at the heart of Spark is the Spark core, which is the engine where most of the analytics happen. And then it could be run standalone, or it could be run in tune with a scheduler. And Yarn, Hadoop's Yarn, or Apache Mesos, or Spark comes with a standalone scheduler, which is a Spark scheduler that could be used. So you could run Spark in a clustered environment. And then with respect to storage, it can handle local machine, Hadoop distributed file system, Amazon S3, RDBMS, or any NoSQL database too. And then Spark comes with a set of libraries, Spark SQL. So you can execute your SQL-like queries and do investigative or analysis or debugging or even prototyping. And then machine learning library, wherein you could run the same set of operations over and over, and which amounts to machine learning capabilities. And then GraphX is the library that lets you process and analyze graph data. And then streaming, of course, is for real-time analysis of streaming data. And then it also provides APIs for many languages, Scala, Python, R, and Java. And then in addition to that, it also provides interfaces to tools to other ETL tools via JDBC connections, so they can query data and perform ad hoc analysis. So this is how the components look like within a clustered environment, wherein your Spark application would be the driver, and at the heart of it is the Spark context. It's like the application context in a Spring application. So it is a client when you see from the perspective of the worker nodes, and it is the master when you see it from the perspective of the application itself. So it works in conjunction with the cluster manager to talk to all these worker nodes, which would be the ones that would perform the actions, perform the tasks, and then report back to the driver. And then the master node would be the driver program, or the master, and then the workers would be the slaves. So the life cycle of Spark is that data, be it through streams, data sources, DB, a flat file, CSV file, a graph, it goes through the Spark engine, and then transformations and actions are applied on the data, and then that data could be stored in the DB for later viewing or for later retrieval, or it could just be served up to a dashboard or a UI for real-time consumption. So these are some of the important concepts in Spark. We've already seen what Spark context is. It is the heart of the Spark application. And Spark context is created from Spark configuration. Spark configuration, it has three properties. What is the master? What is the memory that is allocated to do the processing? And the name of the application. Spark configuration now creates Spark context. So Spark context can talk, can enable access to cluster management, the cluster manager for the driver. And then there is RDDs. You deal with any kind of data that gets into Spark has to be converted to an RDD for it to process it. An RDD is nothing but a data set. A data set is nothing but a collection of data items. It's distributed in the sense that you could split it up, partition it, and then feed it to various worker nodes. And it's resilient in the sense that it's not mutable. It's immutable. You cannot change the value. Once you create an RDD, you perform a transformation, that will result in another RDD. You cannot modify it in place. And DAG, directed acyclic graph. So whenever you create an RDD or perform a transformation on an RDD, what Spark does is it creates a DAG for it. A DAG is nothing but a graph with a set of vertices and edges. Vertices are the RDDs. And edge is the operation that you perform on the RDD. So if you see a graph with two vertices and an edge, so an RDD would move from point 1 to point 2, and then the operation that's performed on it also shows you the direction in which the RDD is moving to in terms of transformation. And then, of course, there's broadcast variables and accumulators. So one of the reasons why Spark is fast and highly performant is because of these. For instance, if you have something that you are using very frequently in your application, then it's always best that you have a constant, store it, and then reuse it. Through broadcast variables, what it does is lookups are a good example for it. It stores them as a broadcast variable, and it cannot be modified by the worker nodes. So it just ships it off to these worker nodes, and then they use it. So you don't lose a lot of your resourcing power via reading and writing to the disk. And accumulators. Accumulators is another variable that is only read by the driver. The workers can write to it, but they cannot read it. That variable is only available for the driver to read and the workers to update. So it's mostly used when as counters when you're going through loops. Then you have an accumulator that the workers will write to it, and then the driver has access to it to see what's happening in terms of processing. To delve deeper into a resilient distributed data set, it's immutable, like we already discussed, and it could be partitioned and distributed across multiple nodes. So parallel processing can happen on it, and then it could be cached and persisted. So when you cache an RDD, you are caching it in memory. And then when you can persist it to local storage or to HDFS or Amazon S3, wherever you want it to. And then if you want to release memory for other processing, then you can uncache or unpersist it. And there's two sets of operations that you could perform on an RDD. One is a transformation, one is an action. A transformation, when you do on an RDD, it would result in another RDD. And when you perform an action on an RDD, it would return a result, a value. So examples for a transformation is map, filter, wherein you would end up with another RDD. Count, or reduce, or min, max. These return a value, and that's an action. So another performance gain that Spark touts is lazy evaluation. So when you create an RDD, it does not create it right then. Unless you perform an action on that RDD, it would not create the RDD. So at the time when an action is invoked on that RDD, maybe it's a little slow, but then later on when that RDD is used, it's fast. So when an RDD is created, what Spark does is it creates a DAG for it. And when it creates a DAG, it ships it off to the DAG. It's there. It creates the operations that need to perform, and then it creates the map with all where the RDD should be after the operations are performed. And then when an action is invoked on that RDD, what happens is Spark would give this DAG to the DAG scheduler. The DAG scheduler would then split this into different stages. And then it would give it to the task set scheduler, which identifies the tasks, and a task would handle a unit of work, which is the basic unit. So it divides it up into chunks and then handles it in a way that it's parallelly processed and fast. Mm-hmm. So Spark is built on a similar, it's built on HDFS, which is Hadoop file distributed system. So Spark and Hadoop, they are in the same business, but Spark is way beyond Hadoop. And the reasons are Hadoop only handles batch processing, so there is a latency to it. So if you have data, if you need data, and if you need analysis done on that data in real time, Hadoop doesn't serve your needs. There's Spark, which handles real-time data and batch processing. And of course, the performance is great because you can you make multiple passes through your data without incurring any debt while you're writing it to the disk and then reading it from the disk, because everything is performed in memory. It's 100 times faster in memory than Hadoop. And if you were to do it on disk, it's 10 times faster than Hadoop. Hadoop is all the time. There's only single pass. There's only a few operations. Map and reduce are the operations that you have in Hadoop. And if you have a problem which is non-trivial, you cannot express it in terms of just map and reduce. Spark has about 80 operations that it can perform. And in conjunction with Apache Pig, I think it has even more. So Hadoop spends most of its time in processing energies, writing and reading from the disk, and then performing analytics on your data. Whereas Spark does it mostly in memory, and that's where one of the performance gains is. And Spark is very easy to use, and Spark has APIs for Scala, Python, Java, R, and Clojure too, I think. And whereas Hadoop is written in Java, and it only has, and you can only write your applications in Java. And then with respect to deployment too, deploying a clustered environment in Hadoop is very painful, and maintaining it too. Whereas with Spark, it has its own cluster manager, and then it also works with Hadoop's Yarn and then Apache's Mesos. And that is very easy once you set it up. And then, of course, there's low latency because it can handle huge chunks of data, and it's fault tolerant too. And the reason it's fault tolerant is that it's dealing with RDDs. Because it's immutable, and there's no data corruption, there's no race conditions happening there. And also because then you divvy up your RDD into chunks and then distribute it, and say if one of the nodes has a failure, and then that RDD is lost, you can easily recover it because Spark maintains a lineage of these RDDs. So it knows its origins. So when you think that that's lost, it can trace back that lineage and then recreate it. And then, of course, because Spark does most of its processing in memory, it uses a lot of RAM, whereas Hadoop uses a lot of disk storage. So that's costly. So if you want the same processing power with Spark and Hadoop for the same application, then you will have to purchase more machines to use Hadoop, and that leads to more cost. So there was I don't know if it's a competition, but Spark holds the world record in 2014 for the data in a gray category for sorting 100 terabytes of data. So Spark used only 207 machines, and it processed all that data in 23 minutes, whereas Hadoop took a lot of machines and a lot of time for it to process the same information.
Something that I remember Spark was the best way, aside from the one that you mentioned earlier, for the Spark versus Hadoop. I think it's also developer friendly.
Yes, because it has interfaces.
Yeah, it also has this Spark SQL, which is basically the Apache version of SQL. For those who haven't dug into the big data area, so imagine that if you do a SQL on a database that has terabytes, because when we're talking big data, you can't really use Spark or Hadoop with like megabytes or gigabytes. You have to go over at least terabytes or petabytes for it to work, for it to be efficient. So if this Spark SQL, if you use, let's say, for example, you use MySQL or MSQL on a terabyte, it would cost you a lot of memory. What Apache Spark did was they tried to create their own SQL, which is Apache High Query Language before, and then they changed it to Spark SQL. And as a developer, you don't have to think in a MapReduce way, but you could think the way you're thinking in a database DBFS knowledge. Like you don't have to think of what's going to be my map and what's going to be my reduce to extract or select data. You could just use your simple select statement from MSQL and use it directly to your Apache High SQL.
Right. So most people, what they do is because they have Spark SQL, they write their queries, and then they query the data for experimental purposes, for investigative purposes, or for even building prototypes. But then when you have this application built out, and if you run it, and if it's running on huge amount of data, and then if you hit an error, then you'll have to redo all that. So for purposes wherein you're just trying to study the data, a sample of it maybe, then Spark SQL comes in handy. But then when you have to have an application that you fault tolerant be run, then you will have to ship all of this into a library and then have your application run within the Spark context. And then the other thing is Spark is written in Scala. Scala is a language that's built on Java with functional programming concepts and immutable data. And also it does not engage in loop and other control structures. Between Scala and Python, Scala is, for you to adopt Scala or Python with your Apache Spark, it's easier if you go with Scala because Apache is also written in, Spark is also written in Scala, but then Scala is relatively new and it has a slight learning curve to it, and also there's not a big developer community, and libraries that are available to work with Scala are also not as many as Python has. So it's, again, a trade-off. Whatever you're comfortable with is what you would go with. And yeah, let's see some examples. So I have Apache Spark downloaded, and and another positive feature to Apache Spark is that it has a command line interface for both Scala and Python. So it's called REPL. The REPL is interface is read, evaluate, print, and then loop. So it takes commands, it evaluates it, and then gives me the result, and then it's ready for to take another command. I start my Spark shell. So with this, when I say master, what I'm saying is my URL is local. So I'm running it on my local machine. So I could specify threads over here, like 5 or 4, but then for now, I'm just going to use just one thread. Okay, so there's some commands like I could do. So the SC here that they gave us is the Spark context. So with Spark context, I could create an RDD, apply transformations on it, and then write it or read from the disk. So for now, let's see what the version of Spark on my machine is. It's 2.2.0, and then I could see what the app name of my Spark is. It says Spark Shell. So the Spark UI that I have it, I can go and see, look at jobs, the storage, what stages they go through, and any SQL that I run. I can go see all that on my Spark UI. And Spark Shell, the application name that you just saw, is the Spark Shell that is here, that by default is provided to me by the Spark context. So I can just say, the way I create an RDD is as so when I create this RDD, I don't see anything over here. Nothing is run over there. When I say collect, what it does is it collects the contents of the RDD into an array. So this is an action. When this action happens, I'm guessing jobs. It's run. The job is run. So when I created the RDD, it's not run, but when I performed an action on it, that's when the RDD is created and the action is performed on it. Let's read a file. I have a file on my machine that I It is. So if I say text file dot, there's no jobs that will run. So if I say count, it displays the number of lines that I have in that file. That's when the other job is run. And if I do collect, it displays the array that the RDD was read into. These are the list of movies that I have. And what I can do is I can count the number of words that are in that file. So what I'm doing right here is I am reading every line. I'm splitting every line by space so that I'm reading every word, and then counting all those words and then making a list of all the words with the count next to them. So when this happens, let's see if there's any jobs that will run. Oh, the collect was the previous action that I performed. So now count that collect. And I do this. Now this is an array of the words. There is the word Ford, and then it occurs one time, and then there is this word that occurs once, and this is an array. So let's try to print them one line after another. So this. So it prints the word and then the count next to it. So I have another file that is that has books in it. So let's see. Let's read that into another RDD and then perform actions like union, intersection, etc. So I'm performing an intersection between these two files. So when you did that, it created another RDD and book. So that's an RDD, and it's so there's I have. Let's go take a look at that. So there's a couple books that I have here, and then out of them, The Hunger Games, The Lord of the Rings, and Harry Potter are the ones that were made into movies too. So I have them. So when you perform an intersection after you read these two RDDs into Spark, so you'll see just The Hunger Games, Harry Potter, and The Lord of the Rings come up here. There's Harry Potter, Hunger Games, and Lord of the Rings. And now you could save this this RDD onto disk by doing save as text file. And then you could mention where you want it saved as. When I did that, let's go and see. So you have books and movies. So part 0000 is the file that it saved the contents into, and you would see that those are the contents of the file. And if you want to partition, if you want to save your RDD into part files, not just one file, then what you could do is say book file. I will go and say partition file is partition it 5 ways. Not a member. An RDD. So by using the action partition, you could partition the books file into 5 separate. So then you would see instead of part 0000, you would see part 0000, 1, 2, 3, and 4 files. I don't know why that says it's not a member of. Looks like that is not available. But this distribution, I'm not sure. So we could go through some more examples wherein you could just read arrays and then perform Cartesian products on that, union, intersections, distinct, subtract. These are all the transformations that we could do. Let's go with a num array. And I'll have a character array. See that then it does a Cartesian product of both those arrays and then creates another RDD. So you could go on to perform union. It's all similar.
Since it does everything in memory, what if you have like really large data sets that don't fit?
So then it also makes use of the disk to an extent, and then I'm not sure.
Okay. I think it's something to do with, that's why I use the streaming, so that you do it bits at a time. If that's
So it's really an arbitrary framework processing data sets.
Yeah.
And it'll break it up into pieces, and each of the pieces gets loaded into memory. So
it'll partition it, and then it'll perform basically like a merge sort in memory for each piece. And then, really the smart of the framework is how it breaks that up into each of the pieces and how it optimizes.
So it's always breaking it up into something small enough to fit in the memory section.
It's arbitrary. So you tune performance by changing the structure of the way that it gets deployed.
Okay.
It's one way to tune it. So you can say, give me this many machines with this amount of memory, and then you can tweak those settings and numbers of machine, how much memory each machine has to see how it affects your data set. And that's going to be based on the types of operations that you're performing.
Any more questions? And these are some of the resources that I went through to study up on Apache Spark. So we have Spark, Apache, or that's where I downloaded from, and then there's a lot of documentation for Scala, Python. It was really helpful. We are done if you guys don't have any more questions.
In what scenario would you not want ARDB?
Spark does lazy evaluation. I don't know if there is a configuration where you could say that I don't want lazy evaluation, but I haven't heard or read of that happening. Okay. So by default, there is lazy evaluation. That's one of the ways that it gains an upper hand with respect to performance and all that. Okay.
The record stop.